Okay, ladies and gentlemen, let's get started. Little orientation this morning, where we are and where we're going. We are going to dive into Lecture 10 today. And when we finish Lecture 10, we will be finishing our Minimal Cognition Robo-Olympics here, where we're looking at evolving robots and testing whether we can actually get them to perform a various number of tasks or events, which each one is a building block of intelligence. As we found at the beginning of the course, it's kind of difficult to define what you mean by intelligence, but usually you can articulate a list of things that you would like to see an animal or a human, or in our case, a machine, be able to exhibit if it actually is intelligent. So we're going to finish Lecture 9 today. We were looking at 4 events last time. We just started the 4th and final one last time, so we'll jump back to Lecture 9 in a moment. And we'll look at a 5th task today. It'll probably take us most of today to look at that particular task, which is active categorical perception, or ACP. That will finish our sort of sub-theme here on minimal cognition, and we're going to switch gears and look at another important aspect of intelligence, which is definitely specific to robotics, which is getting yourself from point A to point B, right? Our world is filled with machines, but one of the things that distinguishes robots from all other machines is self-motion, the ability to move from one point to the other. This is a tricky thing to get machines to do, so we're going to start in Lecture 11, which we may actually get to today. We'll see how we go, is legged locomotion. So if we want to get around in everyday environments, not just factories, there are stairs, there is rough terrain, there's ice out there today. Legs are a good way to deal with the outside world, so we're going to look at that today. So we're going to come at the beginnings of cognition, starting in Lecture 11, from a very different direction. We're going to start with simple machines that can just get themselves from point A to point B, and then could we start to leverage on top of that all the other aspects of cognition. Okay, that's where we are and where we're going. You're working on assignment 5, which is getting you to refactor your code and make it a little bit more object-oriented and modular, which will make it easier for you in the coming assignments, because we're going to start to build up our code base quite a bit in assignments 6 through 10. Any questions about the assignments? We're all good? Okay. So back to Lecture 9, and again, we're sort of looking at this Robo-Olympics and looking at these different tasks. We looked at the first one, which was perceiving affordances. What is an affordance? Yes?
It's what you sort of project, what you project onto an object, sort of how you see it could be used.
How it could be used.
That's like a sentence, but you know.
Yep, I know exactly what you mean, yes. So thinking about objects in terms of how you might use them or how you might use them, or that's an affordance, right? So usually it's talked about as the object is the one that is doing the projecting. It's advertising an affordance to you. We looked at that. We looked at self-non-self discrimination, which seems like an easy thing to do. Segmenting yourself from everything else that's out there. We looked at a short-term memory task, so getting the robot to have to remember. This 4th one is the most difficult one, which is selective attention. And I started last time by explaining it to you. We've got our little robot, again, moving back and forth along the bottom of the screen. It's got these 2 rockets, so these 2 motor neurons, which are controlling the 2 rockets. It has 7 ray sensors, and these 2 objects, which in this task are going to fall independently. They're not attached. They can fall at different directions, indicated by the dashed arrows here, and they can fall at different velocities. So in this picture, the black object on the right is actually further from the robot, but the longer dashed arrow indicates that that right-hand black object is going to fall faster than the closer one. So the robot has to selectively attend or pay attention to these objects and choose, again I'm putting it in quotation marks because we don't know how the robot actually does that. It's going to have to choose which one is going to hit the ground first and where and when, and get there and capture it, which is simply just be there when the object hits the ground, and then remember where the other one was and go and get it. So the fitness function, which is on the right-hand side, looks very much like what we've seen before. We're going to sum up over a number of trials, P sub I, which is the performance of the robot in each of I trials. And P sub I is now the sum of D sub I1 and D sub I2, which is the distance between, DI1 is the distance between the robot and object 1 when object 1 hits the ground, and D sub I2 is the distance between the robot and object 2 when object 2 hits the ground. What's the best possible thing that the robot can do? What do we want the two D sub i's to be? To be 0, right? 200 minus 0, so the best you can do in this task is 200. Okay, in the process of evolving robots to perform this task, there are 0, 1, or 2 problems that can arise. So depending on where we place these two black objects and the direction they fall and the speed at which they fall, there may be the passing objects problem, which I just described to you, which is an object which is further away, moves faster, and hits first. So the passing objects problem. The other one is the object permanence problem, right? Our robot is pretty poor in terms of its visual capabilities. It's got this narrow cone of perception. So as it moves back and forth, the objects may actually fall outside of its field of view, and it may no longer be able to see the objects. So it's going to have to remember where they are. Remember that these robots have these little CTRNNs inside them, these particular kinds of neural networks that also have some recurrent connections in those neural networks, so the robot can remember. It's going to have to evolve the ability to do so. So far, so good? Okay, everything we've seen in lecture 9 here, this was done 18 years ago. This is a rather old paper, so there weren't, unfortunately, videos of these robots in action, but I had a student who took this class a few years ago and tackled this particular task in their final project and did us all the favor of leaving a video. So you can actually see how this works. We don't have rockets in PyroSim, but we do have wheels. How's the robot doing at the task?
Good.
Not too bad. When does the robot decide which object to chase? Trick question, right? It's kind of hard to tell. You see the right-hand object it no longer sees, but remembers at least on what side that object was on and moves over there and is able to capture it in time. There's the object passing problem and the object permanence problem. Okay, not bad. Yes?
Do the two objects have to initially start within the rate sensors of our region in order for this to work?
They do not. So I just paused it here in this case. You can see in this case some of the objects start beyond the robot's field of perception. I'm not sure whether in the actual experiments reported in this paper that was the case, but the student that implemented it still works. Okay, so that's what we're trying to get the robot to do. Let's see if we can analyze a little bit more about how it actually did so. So again, like we've seen before, we are skipping over the evolutionary part. We assume we've done all the evolution. The experimenters took the best evolved agent they had and pulled it out of evolution and then replayed it many times. In this figure, we're going to watch the robot played back in 5 different situations. And we're going to make these 5 situations more and more difficult. We're going to start with the task in the top left, where there is neither the passing objects problem, not PO, and not the object permanence problem, not OP. So in this case, because we don't have the passing objects problem, the object which is closer is the one that's going to hit the ground first. And we do not have the object permanence problem, meaning that the robot is able to keep both objects in view at all times. It could go somewhere else and lose perceptual contact with them, but if it stays in the right place, it can always see both. Okay, again, there are some pretty creative visualizations here to try and show you exactly how the robot is doing this. So as you can see here on the vertical axis, we have time, and we have 2 parallelograms. What do the parallelograms represent? Or is this a rhombus? I always get them confused. Whatever they are, we have 2 polygons here. What do they represent?
Is it the vision of the robot, where the robot can see the object?
Where the robot can see the object. So in each picture we have two of these polygons, light gray and dark gray. So they correspond to the two objects. So I'll talk about the light gray object and the dark gray object. Okay. The cone shows what the robot can see. So in the first case, we have this light gray. Polygon, and we have this squiggly line back and forth. What do you think the squiggly line represents? This we've already seen in some of the previous figures.
Path the robot took.
It's the path the robot took, right? What about the straight lines?
The straight lines would be the falling objects, but would
The motion of the objects themselves. That's
not
right.
really the path of the robot, though. It's more like the position, the X position of the robot plot versus the Y position of the object.
Exactly. So the Y position is time, and remember our robot can just go back and forth. So it is the motion, horizontal motion of the robot over time, right? Okay. So what we can see, if that squiggly line stays inside of the light gray polygon, what does that mean? Or alternatively, if the line goes outside of that polygon, what does that mean? Can't see it anymore if it goes outside, right? So this picture is showing us what the robot is able to see at every point in time. You'll notice that the squiggly line stays within both polygons through this entire evaluation period, which means the robot can always see both objects. Okay. The light gray object hits the ground first, and you can see when it hits, which is when the polygon, it's the bottom part of the polygon. Right? Did the robot capture the light gray object? Yes, the squiggly line lines up with the straight line. It captured it. What did it do after it captured that object? What did the robot do next?
Focus on another object.
Yeah, exactly. It started to head to the right towards where the other object was falling. That other object was falling away from the robot, right? Gets right underneath it and basically tracks underneath the object until it hits, right? This robot is doing a very good job at this task. Okay, so not so surprising, this first task is pretty easy. So let's move on to a second environment now. And now we're going to introduce the passing objects problem. So in the second picture, we still see that the light gray object hits the ground first. But we know we had the passing objects problem, so that means the light gray object was originally higher than the dark gray object, and they passed at some point. How do we know when they passed from this figure? The dashed line is telling us exactly when the objects passed one another, right? Below the dashed line, the light gray object is now below the dark gray object, and then a short time later hits the ground. Before the objects passed one another, did the robot know which one was going to hit the ground first?
Hard to tell.
As always, hard to tell. What was the robot doing during that period?
Determining position and speed of the objects.
Possibly. Determining, that might have been what it was doing. It's hard to say. All we know is really the motion. Yep.
He's staying sort of in between both of them.
She is staying in between it, I don't know, staying in between both of them, right? Sort of what anyone would do, right? A tennis player is waiting, which side of the net is it going to come over? Who knows, right? It's sort of bouncing back and forth underneath both. So you might conclude from its behavior that it doesn't know, right? Now, it's hard to say. If the robot did that a little bit and immediately moved over and was tracking the light gray object, then you might say, okay, it looks like it knows. Even before it can figure out, even before the light gray object has passed the dark gray object, it could figure out that this one is going to hit first. How would it know that? Simplest thing is just go after the thing that is closest to you. But this robot could, in theory, figure that out.
Isn't it sort of like when you send out sort of a beam and it's determining how fast it comes back, you can determine the speed of the object, so it could determine the speed of both of the objects and see which one's really
It could if it was able to detect, sending out a light pulse, for example, and getting it back. It doesn't. These ray sensors have, infinite speed, so it doesn't have that available to it.
Well, if they're the same size, then the one that's closer to you will appear bigger, so it will block more of the ray sensors.
Possibly, but above the dash gray line, it's the dark gray object which is closer to it, right? But that's not the one that's going to hit first.
If you measure from one time step back, the change, you can get speed and I guess distance might be a little harder, but possibly, like you were saying, with different, how many of the ray sensors are occluded, you could probably get an estimate of speed and direction.
You probably could get an estimate of speed and direction, right? But you have to take readings at 2 different time steps, right? So the ray sensors are only giving you position, right? How long is the ray step? How long is the ray sensor at that time step? But because these robots have CTRNNs inside, which have recurrent connections, there is the capability of memory, and it could remember where the object was at the previous time step, and the difference between the length of the ray sensor gives velocity information. In theory, it could do it. It seems in this case that it's not, or again, it's hard to tell, but it's seems like it's not sure, right? Back and forth, and then the objects pass one another, and what happens at that point?
The robot captures whichever one's coming closer and faster.
Yep. Yeah, it eventually captures. Eventually captures the light gray one, but it takes a little while to get over there, right? So who knows? Maybe it's still unsure. Again, in quotation marks. But it eventually figures it out. When it captures the light gray object, it's still, the squiggly line is still within the dark gray polygon, which means it can still see the dark gray object and goes chasing after it and tracks underneath it and captures it successfully. Question?
Yeah, I'm blanking on this. Do the ray sensors return distance as well as direction?
They do not. The ray sensors only return distance. So the robot has 7 of these ray sensors, and at every time step, all it gets is 7 numbers, like your robot also.
And then the direction is the direction of the ray sensor.
Yes, exactly. By polling the different numbers, it knows the direction of that ray sensor.
Okay.
The leftmost ray sensor is now shorter than it was before. That kind of information. Yes. Okay, let's look at environment 3 here. Again, it's the same evolved CTRNN. No passing objects problem now. So the light gray object is initially closer to the robot. It's going to hit the ground first. The robot seems to be underneath both and is maybe kind of not sure. Seems to sort of track over to the dark gray object, but then back to the light gray object, tracks the light gray object and captures it. And we can see that the squiggly line is now outside of the dark gray polygon, which means the robot cannot see the object. Does the robot remember where the dark gray object is? And how do we know?
Well, at least remembers which side it's on, because it heads over that way.
It remembers at least which side it's on. Yep, because it doesn't seem to have any hesitation, right? At the end, immediately after capturing it, it goes streaking back over to the left, and at this point, it sees the object again. If you look carefully, there's a little kink in its direction, so it accelerates a little bit faster the moment it sees it, so it sort of hustles to get over there and gets under it just in time to capture it. Well, with some time. Okay, let's make things really hard now. So now we're going to put together the passing objects problem and the object permanence problem. Above the dashed gray line now, in this 4th environment, we can see the robot does more or less exactly what it did in the 2nd environment. It's tracking back and forth, right? Which object is it going to select to attend to? Which one is it going to pay attention to and go chase after, right? This is why this is a difficult task. Selective attention, this is something that we all face every day. And in our wired world, it becomes more and more difficult, which is what to pay attention to, right? Your phone may be beeping a notification to you right now, but hopefully you're trying to pay attention to the front of the room. Things out there in the world are always vying for our attention, and any intelligent agent has to select and decide what to pay attention to at what point in time. Not always an easy thing to do. Okay, so what does our robot do? Well, it figures out, again, that the light gray object is going to hit the ground first, and goes chasing after it, captures the light gray object, and then immediately goes after the dark gray object, which is quite away from it, and traveling further away all the time, so goes streaking back to the right and gets there just in time to catch the dark gray object. Well done, minimally cognitive agent. Let's be really diabolical now. So now we're going to still have the passing objects and object permanence problem, but they're going to be horizontally separated from each other a little bit more. And if you look at these two polygons and compare them to these two polygons, these two overlap only in this region. So there is only a very small place and for a short period of time during which the robot can see both objects. After that time, or outside of that area, it can only see one object at a time. What does our robot do? It has to remember, yeah?
Well, since it remembers the speed and direction of both the objects during those two time steps that it originally sees, then we can go find the robot that's gonna come closest first, grab that one and go to that position.
Absolutely, which is what it does. And the investigators were somewhat nice that they started the robot near that place at the beginning where it could see both. And it may be difficult to see in this, but it definitely spends a fair bit of time in that area. So it's not moving too quickly at the beginning. That line is somewhat vertical, meaning it's not moving very much. So it's definitely trying to capture as much information as it can about both objects. And then even before the light gray object has passed the dark gray object, the robot goes chasing after the light gray object. Right? They're falling far apart from one another, so it's got to make a decision quickly about which one. It doesn't have the luxury of time to wait until the objects pass one another. It's got to figure out velocity and direction quickly and predict which one is going to hit first long before it does. Go get it, and then remember where the other one was and go back and grab it.
Were they able to predict if it was just remembering to go the other direction, or whether it actually... Because
That's an excellent question.
One coming like this, another one coming faster from the same side. So you're saying they weren't able to tell if it was just remembering to go the opposite way that it went at first?
We don't, as usual, we don't know, right? Either explanation fits, right? Maybe all it needs to do is remember which side. And in all the cases it saw, hopefully they were easy enough that if it moved at this particular velocity, and it looks more or less like it's always, no, not always. This case, it's traveling a little bit faster than in this case. Most of the time, it's traveling about the same speed. So maybe all it's doing is being lazy and just remembering which side it's on and moving at a good clip so that it gets within perceptual range of the other one, and it can correct what it's doing to make sure it's in the right place at the right time. Hard to say. Maybe it is actually remembering where it is. The fact that the velocities are different might be a clue that actually it has an idea about how far it has to travel in a given period of time. We don't know. Okay, so is this robot intelligent? I don't know, but this is definitely an important aspect of intelligence. It's certainly simple, but our robot is embodied, right? It's got sensors, it's got motors, and it's using its own motion, sweeping its sensors under the undersides of these objects, and combining motion of self, motion of other. It's combining memory, attention, putting all these things together to perform this task. Question?
Yeah, it might be like a little bit picky, but like
Yep.
just at the end of that last, you were saying something, and you said we don't know whether it remembers the distance and whatnot.
Correct.
And so, like, if we built this robot, we were professionals, the best out there looking at neural networks, and we went in and looked at it, like,
Yes.
could we determine if it knew that, or
Uh,
do we not know?
Could we pick apart the neural network and actually see inside that it knows not just which direction the object is, but where? The short answer is no. That's a very difficult thing to do. There are papers being published last year, this year, about that topic. Can you understand where in a neural network a representation is, which in our case, a representation might be the object is going to hit at that point over there at this particular point in time. Very difficult to pull those things back out of a neural network. Now what we could do is perform an experiment. We could take this particular case and drop the object moving at a different direction and see whether its velocity changes. Right? I think someone was mentioning this before. If the object which is outside of its visual range is falling at different velocities in different directions and it changes its behavior, then that has to mean that it's remembering details about the particular object. If it always heads to the right at the same speed under all conditions, then it's probably not remembering exactly where it's going to hit. So you can do sort of things like that, but pulling it directly out of the neural network, difficult, not impossible, but difficult. Okay, so again, we have a robot which has all the basic building blocks: sensors, motors, neural network, memory, and it's interacting with its world, but this is just about as simple as you can possibly get, right? Okay, so now let's move on to lecture 10, when we're going to look at a fifth component of intelligence. And this one is probably the most difficult of all the ones we've seen so far. This is active categorical perception. So we know obviously what perception is, seeing the world. Active, so the robot is going to use motion to try and categorize the objects that it perceives in its world. So we're going back to our discussion about embodied cognition. So just to set up what active categorical perception is, passive perception is what it feels like you're doing most of the time, which is sitting quietly and listening to me and looking at the slides. Stuff is coming to your eyes, you don't need to do, or your ears, you don't need to do too much, right? Active categorical perception is you actively reach out in the world and manipulate things to try and learn about the world around you. We've already seen this a couple times now. We saw this with BabyBot manipulating the fruit on the table in front of it. Can we evolve a robot to perform active categorical perception? Before we look at the robot to do that, there's an additional detail about active categorical perception that's kind of interesting, which is the very fact that you have a body and you push against the world and observe how the world pushes back. There's a little bit of magic that starts to happen when you do that. There's lots of different examples you can think up to do this, but let's imagine that I were to give you these 11 objects, and as you can see, they range incrementally between round objects up to edged objects. I put a blindfold on you, and I ask you to categorize these objects into round and edged objects. Sounds like a strange thing to do, because there is no clear dividing line between the round and the edged objects, right? You could say, all right, everything to the right of my hand is edged and everything to the left is round, or I'm going to make the decision boundary here. It's kind of arbitrary, right? There are no two categories here of round and edged objects, just these 11 objects that are more or less round. Let's imagine that, nonetheless, I forced you to try and categorize these into two groups. As you interact with these objects, depending on how you interact, these two groups sort of pop out of the world. So you might, for example, put your hand on the top of an object. So I'm going to give you one of the 11 objects at random, and you're going to tell me, is it a round or edged object? You might place your hand on the top of the object and then push the object left and right. What's likely to happen? You've all manipulated lots of objects in your life. What do you think would happen?
If it's a round object, it would roll easier, and if it was not, it had like bump, bump, bump as you moved it.
Okay, so it might roll easier or it might bump, 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 right? So easier is an adverb, right? So we're still not going to get categories because now we have roll more easy or less easy.
About roll versus slide.
Roll versus slide, right? So depending on how you manipulate it, exactly, you might get this continuous change from one object to the next. But if you push down a little bit harder while you're doing this, and you do this on a rough surface like carpet, you might get the first 3 objects that roll, and then the 4th through the 11th object slide. Actually, not carpet, the opposite. We want something that's relatively smooth, so they will slide. Now, depending on how you interact, that decision boundary is going to appear at different places. The point I'm trying to make is that suddenly these two categories will arise, rollable or slidable. They'll arise based on the way that you interact with them. So categories are not really things that exist out there in the world. We impose them on objects, again, not just based on their geometry, but based on their affordances. When we think about objects and we imagine all the ways we might interact with them, or maybe we actually interact with them, categories start to arise. Things are rollable or slidable or edible or inedible. The categories that matter to us are not so much about the objects themselves, but about how we interact with them. Yes?
So I was thinking about it, my first instinct would be to like put my finger on the pointy part, on the right between two edges, and see when it started to hurt.
Okay.
And then I realized, well, that kind of goes towards like my own fitness and my own health and staying alive. And so I think that also like followed through with the edible versus non-edible.
Absolutely.
But does that kind of thing, is that implemented into robots learning sometimes? Like
we could. Hard to figure out how to get robots to feel pain, and we haven't done that yet. Maybe we don't want to do that, but that is a great example, right? That's just another kind of interaction, which also will give you these two categories, right? Something that causes you pain and something that doesn't. There are different interactions, and they give you these different categories, but you still get two categories, different cases. You might say, I can't even feel it, or this is uncomfortable, and this is painful, and now we have three categories. The point is, again, these categories arise based on your interaction. They're not inherent in these objects. There are no categories here. Just a smooth gradation between this object and that object.
When trying to contextualize objects, like via an affordance for a robot, is it often that we get this perverse instantiation that they don't categorize things the way we want them to?
That's a great example of perverse instantiation. They might interact with objects and form categories that are relevant to them, but have nothing to do with the categories that are relevant to humans.
So how do you change its context?
How do you change its context? That's a great question, and we're going to come back to that in about 10 lectures time. So hold on to that. We will come back to that. So this is actually a big part of the discussion now about robot ethics and AI safety. If we want robots to be able to reason about the world and act in our best interests, maybe not their best interests, but our best interests, they better be able to reason about the world in the same way that we do. And again, that seems a little bit hand-wavy, but what that really means is they better be able to think about interacting with the world, or think about how we might interact with the world, and think about the same kinds of categories as us. Right? It may not be painful to the robot, but the robot better be able to think of that object and that human, and putting those two things together is going to be painful for that human. That's really important.
But then, isn't it much more difficult to provide the robot with empathy than to contextualize it within its own self?
Possibly. So hold that thought about empathy. Again, we'll come back to that when we look at robots that try and see the world in the same way that we do. We'll come back to that. Okay, for now, we're going to just focus on ACP. We just want to see whether we can get robots to interact with the world and form categories. And they're going to do this, again, we're going to evolve robots that have C-tier and Ns. And those C-tier and Ns are going to get the robot to interact with some objects, which we'll see in a moment. And the way in which the robot is going to move is in a particular way. The robot is going to try and move in such a way that it reduces within category differences. So BabyBot has a whole bunch of red apples placed in front of it. They're not the same apple, they're different apples. But generally, BabyBot realizes that, okay, apples tend to respond to actions in more or less the same way. So it's reducing all the slight differences it might perceive when it interacts with a whole bunch of apples. But it figures out ways to interact with apples that magnify the differences between all the apples we put in front of the robot and all the bunches of grapes we put in front of the robot. One good way to do that is, right? These things over here in one category are easily crushable. Grapes, apples, not so much, right? So it's not just any action that will give rise to categories. There are certain actions that will reduce within category differences. When I roll my palm across the top of these objects, they're all going to eventually start rolling. So the differences between these objects, for example, are going to disappear from my perceptual point of view. And these are all going to slide, so the slight differences between all of these objects are going to disappear when I interact with them, and the differences between them are going to become much more apparent. Sounds like much ado about nothing, but this is a very difficult thing for a robot to do. If you really think about the world around you, everything looks different. All of the light, all of the photons that are falling on your eyes, the combination is unique from 1 millisecond to the next, right? At the point of view of your eyes, everything you see at every instant of your life is different from everything else. So everything from your eyeballs inward to your brain is working to try and reduce intra-category differences and magnify between category, reduce within category differences and magnify differences between categories. Okay, so again, thinking about thinking is misleading. This seems like an easy thing to us, but it's actually quite tricky. Yes?
When trying to focus, like, humans have like like everything outside of a very small range is very fuzzy.
Yes?
Do you think that could help like a robot focus on what it wants to?
Possibly. It might help focus and sort of get rid of all the noise, but even within your small focal area, when you foveate on the small piece that you focus on, that combination of photons is also unique from one instant to the next, right? The world around us is very rich with color and motion and shape and all sorts of things, right? Got to reduce those differences. Okay, so this is kind of a strange experiment to have in the minimal cognition experiment because this robot is definitely not minimal. We're getting into a pretty complex robot here. So the reading for today is being drawn from the research paper that describes this experiment. This experiment is about an anthropomorphic robot arm. So anthropomorphic in that at least the arm, this robot is just an arm, they tried to make it somewhat human. Definitely not human, but much more than the minimally cognitive agents that we just saw. So in the top left there, if you look carefully, you'll see that the robot arm is made up of seven joints. Some of these are familiar to what you've already implemented in PyroSim. The shoulder and elbow joints make a lot of sense. You'll see there are 2 joints in the shoulder. Why 2 joints in the shoulder and only 1 in the elbow? Exactly, right? So your shoulder doesn't just move through one plane. Your elbow does. Your elbow moves your upper and lower arm through one plane, but your shoulder moves through 2, really. So nature solved that for us with a ball and socket joint. You can also do it relatively simply with 2 rotational joints, which have their joint normals perpendicular to one another. So as signals are sent to J1 and J2, the shoulder can do this. It can't do the third one, but that's good enough for our robot here. You'll notice that there are also some joints midway along the upper arm and the lower arm. That seems a little bit strange. What are they doing? It's not this, that's the wrist.
Is that so it can rotate?
Rotate, right? So you can hold your upper arm more or less straight and rotate your lower arm and your hand along the long axis of your arm. That's what J3 and J5 are doing. They're twist joints which are rotating things along the long axis. Yes?
With the double joint in the shoulder, can they like rotate?
Absolutely. So I can send commands to J1 to do this, and at the same time I can send commands to J2 to do this, and if they're doing it at the same time I can move.
That's the exact same as a person.
Not exact same as a person because the robot cannot do this, cannot rotate about the third axis. Okay? Okay.
You could add a third joint in.
You could add in a third joint and approximate that. Yeah, exactly. 2 joints, J6 and J7 at the wrist, makes sense. And then we get into the hand, which is a little bit more complicated. And if we look carefully, I think, let's see if this is clear from this picture. We might have to look at the neural network for a second. Sensors, hand, proprioceptive. So it's not exactly clear from this picture, but there are 5 motor commands sent to all the joints in the hand, and there should be 3 joints per finger. You also have 3 joints in your finger, but you cannot move all 3 joints independently in the same finger. So they made this anthropomorphic in the same way that they took the signal from a motor neuron, and they had 5 motor neurons, 1 for each of the fingers. And when that motor neuron receives a value, it sends that same value to each of the 3 joints in the finger. So all 3 joints in the finger move in the same way. So we have 15 joints, but 5 motor neurons assigned to them. Make sense? Okay. This lecture is a little bit of an anatomy lesson for you as well, right? You can sort of figure out what's possible and what's not. Okay, those are all the joints. We'll come back to this in a moment. We'll come back to the sensors in a moment. Let's talk about the task. We have our robot here, which is the single arm, and we're going to try and evolve it to perform active categorical perception. And we're going to cheat a little bit in that we're actually going to form the categories beforehand. We're going to have just 2 categories. We're going to have spheres and ellipsoids. And we want the robot to figure out how to interact with these objects to determine which of the 2 objects we've placed in front of the robot. So it's not free to come up with its own categories, but it's free to come up with the kinds of actions that will reduce within category differences and magnitude differences between categories. Okay, how are we going to do this? Well, we're going to evolve CTRNNs, populations of CTRNNs, like we've been doing all along. We're going to take each CTRNN, and we're going to run it 16 times. 8 times where we start the robot arm in this initial configuration, position A, and another 8 conditions in position B. And in each of those 2 positions, we're going to show the robot 8 objects. The first 4 objects are exactly the same object. The 5th through the 8th object is also the same object, but just rotated slightly different. So we're going to rotate it and then place it in front of the robot. So from the robot's point of view at the beginning, these are just 8 objects that belong to different categories, and it's got to figure out 4 of them belong to the category sphere, and the other 4 belong to the category ellipsoid in 2 different initial conditions. So we don't want it to memorize particular things. We want it to be able to do it regardless of the orientation of the object and regardless of the starting condition of the arm. So far, so good? Okay, so that's the body of the robot, the task. Let's have a look at the brain. This is a nice slide because it reinforces our discussion about CTRNNs. So we have exactly the same CTRNN here. In the top, it's shown visually, and in the bottom, it's shown mathematically. From here on out, whichever one you're most comfortable with is fine with me, but this is a good way to remember exactly what all those equations and CTRNNs are doing. Okay, let's start with the picture. You'll notice the sensors are on the bottom row here. We have a total of 22 sensors. We have 7 arm proprioceptive which makes sense. We have 1 proprioceptive sensor in each of the 7 joints in the arm. We have 10 tactile sensors, 8 through 17. And if we look at the hand here, you'll see 1, 2, 3, 4, 5, all the way up to 10. So we have 1 touch sensor in the palm, and then 2 touch sensors in each of the 4 fingers. Or sorry, second one is in the thumb, 3, 4, 5, 6, 7, 8, 9, 10. So 10 touch sensors in the hand. Like you, most of the touch sensors are in the palm, and we have relatively little sensation on the back of our hand, which makes obvious evolutionary sense. Most of the tactile information you're interested in is about the objects that you're grasping. Okay. And then hand proprioceptive sensors as well. So we have 5 proprioceptive sensors in the hand as well, which I don't think are in this picture, but you get the idea. It's the angle of each of the 5 fingers. Remember that proprioceptive sensors give us back information about the angle or the position of a given joint. Okay, all of the 22 sensor neurons are wired up to whatever that is, 7 or 8 internal neurons, which are the hidden neurons. What does that circular arrow tell us?
Is that a neuron from memory?
It's a synapse, a recurrent connection, a recurrent synapse, which gives the robot memory, if it needs it for this task. It's not clear if you think about it whether it's actually needed. They just threw it in case the robot actually needs it. Okay, so we have our 22 sensor neurons connected to our eight internal neurons, hidden neurons, and then the hidden neurons are attached to a bunch of output neurons. Let's start with neuron 31 through 44. So those are 14 arm actuators, which seems strange because in the arm we have 7 joints, but we have 14 motor neurons. We have 2 motor neurons assigned to each of the joints. That seems strange. Why did they do that? Kind of seems like overkill.
That's what we have too, right? Because we have something that rotates in one way and something that rotates the other.
We have one muscle group that pulls in one direction and another muscle group that pulls in the other. So this is known as agonist and antagonistic muscle groupings. Agonistic. So you have a bicep which pulls in and a tricep which pulls out, right? So they're simulating with those 14 motor neurons the agonist-antagonistic pairs for each joint in the arm. They don't really need it. They could have a single motor neuron that outputs positive and negative numbers to a joint. They're trying to be as anthropomorphic as possible. Okay, so 14 motor neurons assigned to the arm, and only 2 motor neurons assigned to the hand. So I apologize, I misspoke. There isn't 1 motor neuron assigned to each of the 5 fingers. There is 1 motor neuron assigned to all 4 fingers, and the other one assigned to the thumb. So our robot can basically do this kind of thing. So it doesn't have independent motion of the fingers. I don't know why they did that, but there you go. Okay, then we have neuron 47 and 48, which are going to be used for the robot to signal categorization. The robot is going to use these 2 neurons to decide, is the object that it's manipulating a sphere or an ellipsoid? For most people, when you read this paper the first time, it seems obvious, right? What they're going to do is when the robot starts to manipulate an object, if neuron 47 is more active than neuron 48, that's a sphere. And if neuron 48 is more active than neuron 47, the robot is telling us this is an ellipsoid. Makes sense, right? 2 categories, 2 neurons. As we're going to see on the next slide, that is not what they did. Why not? Why not just simply assign an output neuron for each category? We're defining the robot's category. Now remember, we're cheating a little bit in this experiment that we are forcing it to come up with these 2 categories already. So they didn't not do that because we're forcing the 2 categories on it. Why not just assign an output neuron to every category?
Did they want to let the robot have some freedom to decide if they thought there was more than 2 categories? Just give it some evolutionary space? Or?
Yes, you're actually going to be able to encode more than 2 categories in these 2 categorization neurons, right? We don't want to assign a neuron to every category because, again, this is a simple experiment, but we want to try and argue that this is scalable. We could scale this up to a robot that's able to form 100 categories or 1,000 or 1,000,000. We don't want to have 1,000,000 categorization neurons. There's a famous debate that's been raging for decades in neuroscience about the grandmother cell. So one category that most of us have is our maternal grandmother. And is there a neuron somewhere in your brain that is quiet all the time unless you see your maternal grandmother, you think about her, you receive a letter from her? Is there a neuron dedicated to every specific percept, every specific thing that exists out there in the world for you? Some people say that's ridiculous because we have so many categories, it would be hard to pack that all in. Others say, yes, there is such a situation. As usual in biology, it's usually a little bit of both. Okay. But we probably don't want to err on the side of complete specialization where we're dedicating specific circuitry to very specific situations. We saw that when we saw the little robot that was shaking the block left and right and up and down, right? We wanted something scalable where we could pack more and more concepts into the same neural real estate. And we're going to try and do that by packing initially 2 categories, but then more categories into just neuron 47 and 48. And we'll see in a moment how they did it. For now, let's switch back to the math. So we have a total of 48 neurons. Remember that this is a CTRN, so that means we have 48 ordinary differential equations that describe how each of the neurons change over time. So as we've seen before, we have y sub I dot. So how is the ith neuron going to change over time? It's going to be influenced by its own tau value, which is going to make that that neuron more or less reactive to its influences. And within this set of 48 ODEs, the first 22 are going to look like this, and the 23rd through the 48th ODE is going to look like this. First 23 just have minus y sub I, which we saw before. That's always going to pull the neuron back to its resting state. And then plus I sub I. So you know what the 23 are, right? These are input neurons. The only thing that's influencing the first 22 neurons is one of the 22 sensors that's assigned to that neuron. G is missing an I. I'm pretty sure this should be G sub I. There's probably a gain that's associated with each neuron, with each input, which would allow evolution, if it's tuning the G sub I's, to tune how much the robot listens to any of the 22 sensors. Okay, I think that's a typo. I'm not 100% sure. Okay, all the rest, the hidden neurons and the output neurons look very much like what you've seen before. We have our tau. We have the weights that are connecting all of the N through M presynaptic neurons to the ith postsynaptic neuron. We take the value of the presynaptic neuron. We add the bias term, beta here, bias. We add it to that neuron, and then we push it through an activation function, multiply it by the weight of influence of neuron J on neuron I, and sum that up. We're missing one component of CTRNs. What are we missing? G, right? So there is no G sub I in here. Maybe the investigators just got lazy or forgot to put them in. Whatever. Evolution's pretty smart. She'll be able to figure it out anyways. Okay. We're going to use the sigmoid activation function, so-called because it draws an S. This particular activation function is going to squash neuron values. This whole thing is going to squash it to values between 0 and 1. That'll become important in a moment. Last thing here is our indexing. So for neurons 20 through 30, we're going to connect the 30 input neurons to each of the 8 hidden neurons. And for the 31st through 48th neuron, for the output neurons, they are going to receive input from the 8 hidden neurons, which is exactly what you see in the picture above. Make sense? Okay, so now we know the body of the robot, the brain of the robot, the task. Last little detail is how are we going to evolve the robot to categorize for us? Okay, here's how we're going to do it. We're going to look at the value of the 47th and 48th neuron, and we're going to look at the value of that neuron over a particular time period, which is represented here. This time period is from the last 5% of the robot's evaluation period with that object. Remember, we're going to take each CTRN and expose it to 16 different objects. In each of those 16 trials, the robot is moving around and manipulating the object. So the values arriving at the output layer are changing, and the values of neurons 47 and 48 are also changing. And if you think about the given values of neuron 47 and 48 at any given point in time, you can think of that as a two-dimensional coordinate in a two-dimensional plane. So if the two values of the two neurons are here, at the next time step, if the two values change, you've moved from one point in this plane to another point in the plane. So let's draw what this might actually look like. Remember also that these two neurons can range between 0 and 1. So let's create a two-dimensional plane centered at 0 and going out to 1. And we have the value of 47 and y sub 48. This is actually the value of this whole thing, but I'm being lazy here. I'm just going to write 47 and 48. Let's imagine at 0.95 times t, so just towards the end, the two values of the neurons are this. At the next time step, they're this. At the next time step, they're this. At the next time step, they're this, this, this. And then at the very last time step, the two values of neurons 47 and 48 are this. So they're drawing a trajectory in this two-dimensional space. So far, so good? Okay. We're now going to create RSC, which is a rectangle around this trajectory when the robot is in the presence of S, a sphere. So let's put a rectangle around this. And we can see the math now. The minimum of this rectangle is here and here. And the maximum is here and here. So we have this rectangle now. Let's imagine that we take the same C tier and N, we remove the sphere, and we put an ellipse in front of the robot. And now it's going to start to manipulate this object, and it's probably going to do something different because its interaction with a different object is different. And it's going to draw some different trajectory like this. And we can put a rectangle around this, which is a rectangle R sub D here, which is a rectangle around the ellipsoid. Remember that we actually are going to do this. We're going to do this a total of 16 times, 8 for the sphere and 8 for the ellipsoid. So we're going to get 8 of these rectangles and 8 of these rectangles. So we're going to put then a bounding box around all 8 rectangles for the sphere. And I won't draw them all. There's a second trajectory for a sphere. There's a third trajectory for the sphere. And we'll put a bounding box around this whole thing. And that becomes C sub S. And this bounding box is the robot's categorization of spheres. That's its understanding of what a sphere is. These are the values that my 47th and 48th neuron tend to take on when I'm in the presence of a sphere. Do the same thing over here. We show it the ellipsoid again. We show it a third ellipsoid, puts a bounding box around all these. I apologize, I shouldn't have drawn outside of 0 and 1. We've got our big bounding box here, and this is C sub D, which is the categorization for the ellipsoid. One detail that I forgot to mention is that in each of these 16 cases, we're telling the robot this is a sphere or an ellipsoid. So we want it to be able to learn or evolve to distinguish between these two categories. After evolution, like we saw in the previous lecture, we're going to take the best C tier and N and play it back in the presence of objects it hasn't seen before. And we're not going to tell it whether that object is a sphere or an ellipsoid. And we're going to see, does it get it right? Does it tell us an ellipsoid is an ellipsoid when an ellipsoid is an ellipsoid? Same thing for the sphere. Can it tell the difference? Okay. How are we going to evolve the robots? We've got the one last piece here, which is the fitness function, and we'll take this in steps. So our fitness function, FF, equals F1 plus F2. So we're going to sum F1 and F2, which means there are two things that we're trying to get the robot to do, F1 and F2. Let's have a look at F1 first. As we've seen before in F1, we're going to sum over all of the environments. So uppercase E equals 16 here, the 16 environments which correspond to these 16 objects. And we're going to, for each one, calculate 1 minus d sub E over d sub max. You know whenever you see a minus sign that we're penalizing for that, the term to the right side of the minus sign. So we want d sub E over d sub max to be as small as possible. What is F1 selecting for? If a robot maximizes F1, what is the robot actually doing? How is it moving? So d sub max, as it says in the caption here, d sub max is the maximum distance the robot can ever get its palm from an object. So this is d sub max for the robot. And d sub e is what was the actual distance between the robot's palm and the object at the end of the trial E. So right at the end, what is the distance between the robot's palm and the object?
Very close.
Very close, right? So we want this ratio d sub e over d max to be as small as possible, right? So the easiest way to do that is for d sub e to be 0, which is this, or this, or this. Doesn't really matter, right? As long as the palm is in contact with the object. So by dividing by d sub max, they're normalizing d sub e to range between 0 and 1, right? So what is the worst possible thing that the robot could do? If it gets an F1 of 0, what is the robot doing in all 16 trials?
It's like not getting close to the object before it decides. It's like as far away as possible.
It's as far away as possible, right? So in all 16 trials, remember from the picture that we actually make things a little bit easy. We start by putting the robot's hand on the object, and in all 16 cases it does this, which is going to be pretty hard to categorize these objects. It has no camera, can't see the object, so it's got to manipulate the object. So we're cheating a little bit with F1 by sort of giving the robot a hint, saying you're not going to be able to tell the difference between these objects unless you actually touch the objects. So touch the objects, right? That's F1. What about F2? Remember, C sub S is a rectangle, and so is C sub D. Tell me about F2.
Is that a 0 if it gets it wrong?
It's a 0 if F1 is less than 1. So let's just focus on that for a moment. Why put that term in there? Why put that condition in there? What are we telling the robot?
If you're not touching it, then you can't categorize it.
If you're not touching it, yeah, not only can you not categorize it, you're not getting any extra points. Even if you, by chance, happen to produce two rectangles that are separate from one another, you're not going to get any points for trying to categorize these because you're not touching them. So learn how to touch the object first, and then we'll give you some additional points here. We'll give you whatever this works out to be on top of whatever you got for F1. Well, at this point, you'll be getting 1 for F1. Okay, so again, let's tackle this equation down here, 1 minus something. So again, we know that the term to the right of the minus sign is going to be a penalty. We want that thing to be as small as possible. What is it? What are we trying to get the robot to do?
We want them to categorize two different things. And the top says like, if the top is small, that means the intersection of them is very small.
Exactly. So what is the intersection between C sub S and C sub D here? 0, right? That's good. Why? Why do we want to separate these rectangles?
Because then it shows it's like actually categorizing things as opposed to overlap. This might be a circle. This might be.
Exactly. So if we have a non-zero overlap between CS and CD, and we put an object in front of the robot, and 47 and 48 trace a trajectory within that overlapping region, the robot is telling us this is a sphere and an ellipsoid. Or it's saying, I don't know, I can't tell the difference. Right? Okay, so we're trying to minimize that overlap, and the best thing you can do is just have them not overlap at all. And again, we divide by the minimum area of either of the two boxes. Okay? We don't know a priori what the size of these two rectangles is going to be. It depends on how evolution sets the weights and the taus and everything else. So what is that fraction going to range between? Should be able to take a pretty strong hint from F1.
0 and 1, because if it's no overlap, it's 0. And
Right.
if you have complete overlap with the smaller one with the bigger one, then the overlap area is the same as the area of the smaller one.
The area of the smaller one, right? So if you have perfect overlap, you have the smaller rectangle inside the bigger one, whichever it is, and you're dividing by the area of the smaller one, which gives you exactly the same value on the numerator and the denominator, 1 minus 1. It's the worst possible thing you can do, is put your categorization for one of the objects inside your category box for the other object. Right? Okay. Let's have a look and see how the robots actually do. So remember that, actually let's back up a little bit. Remember that we're going to show the object to the robot, where the robot starts with 2 different initial conditions, and we're also going to place the robot at the object at different horizontal orientations underneath the palm of the robot. Doesn't make much sense for the sphere because it is rotationally symmetric, but we're going to just do the same thing. We trained the robot on this, we evolved it on this. We got a very high score for F1 and F2 for 1 CTRN in the population. We're going to take that run champion out of the evolutionary process, put that single CTRN back inside the robot, and we're now going to put the sphere back underneath the palm, and we're going to put the ellipsoid back under the palm, but we're going to rotate it to new rotations that the robot hasn't seen before. So we're seeing how well it generalizes. This is not the most difficult thing, but at least it's a start, right? So it's going to see the same 2 objects, but at slightly different positions and orientations. While you watch this video, have a look at the bottom inset here. So there is a blue arrow there. At the moment, at the beginning, it's pointing up. What does the arrow pointing up mean? What is the robot telling us?
It hasn't decided.
It hasn't decided. Even more specific, when they ran this video, you're going to see that arrow move. It's going to either be up, or it's going to point to the sphere, or it's going to point to the ellipsoid. When they created this video, how did they decide where that arrow should be? They're going to run the CTRN inside the robot. And to make the video, they're going to just show us the robot is saying it's a sphere, it's ellipsoid, or it's neither. I don't know.
Where 47 and 48 are pointing relative to those 2 boxes.
Exactly. So as long as the value of neuron 47 and 48 is within C sub S, for that CTRN, the arrow is going to point at sphere. If the trajectory falls, if the value of 47 and 48 is inside this rectangle, the arrow is going to point at the ellipsoid. And when the arrow is pointing straight up, what's the value of 47 and 48?
Not in different boxes.
Not different boxes, it's in neither, right? So the trajectory can clearly go outside of these boxes. In that case, the robot says, I'm in the presence of an object that I don't know what it is, basically. That's how this robot categorizes the world around it. Okay, here we go. Okay, when we started this lecture, I said, imagine you're put in front of a bunch of objects and you roll your palm along the top, and some roll and some slide. If someone were watching you do that, they would clearly be able to figure out what your 2 categories are, right? It's clear. What is the strategy the robot is using here to distinguish between spheres and ellipsoids?
It's rolling the object and then seeing how the object rolls, whether it's smooth or sort of uneven.
Possibly. It's hard to tell, right? If you watch this, the robot is doing almost exactly the same motion for all of the objects. There isn't some, it doesn't start doing something and says, aha, I'm not sure what this is, and there's a very distinctive motion for spheres and a very different distinctive motion for ellipsoids. It's, whatever it's doing, it's kind of subtle and hard to see.
With the ellipsoid, you know, one axis is longer than the other, right?
Yes?
So as long as it hits some portion of that axis, the object should have like a movement that a sphere would not. So if it's rotating about that, I guess diagonal, every time trying to see if it does that, I mean, that would make sense.
It makes sense, right? So it's pulling this object in a particular direction, and the role of that pull, the role that results from that pull is different for ellipsoids and spheres, right? That you can kind of see if you watch the video. It's probably that, right? The robot is trying to maximize differences between these categories, but it's clearly not maximizing it very much.
Well, but he or she is only
Yep.
moving the ball in like one direction, so if you place the lips sort of just right, it might feel like a ball.
Good point, right? So there may be some orientations. This is a pretty impoverished motion, right? You can probably trick it. I bet you could put the ellipsoid under at a particular orientation. Yep.
But does it make sense with the context of the experiment? Because if they're rotating it in
Yep.
each of the 4 different directions,
Yep.
and if it does the same motion every time, it would have to get this exact same like axis rotation, which you can't do within a virtual.
With an ellipse, that it would feel different for all the 4 rotations of the ellipse, right? Which means there's going to be 4 different trajectories inside of the ellipsoid.
Yeah.
But that does not mean that there isn't a 5th one somewhere between those other 4 that is a trajectory that's maybe here, maybe here, maybe here, maybe here. If you were antagonistic, you could probably find some orientation of the ellipsoid that would fool it. I get your point that the ellipsoid, regardless of how it's oriented, always feels different, right?
As long as it does the same motion.
As long as it does the same motion, it's always going to feel different, but maybe it feels more and more different and starts to feel more and more like a sphere. Maybe, again, who knows? Yes?
Even with that rolling, if
Yep.
you were able to trick it that way,
Yep.
I noticed its fingers were trying to move, so wouldn't there be some resistance there?
Maybe the fingers are giving it additional information, says, even just the fall of my fingers over the top surface of the object is already enough to distinguish an ellipsoid from a sphere. Maybe, maybe.
I feel like the closest you could get to that like boundary is if it would roll the ellipsoid completely on its side. So that was like a uniform curve.
That would give you a roll that feels like a sphere, but again, your fingers on top may be different than they would be on a sphere.
Right.
It's hard. You can see, obviously, they picked an ellipsoid with major and minor axes, which are pretty close to one another. So it's, who knows? As always, who knows? Okay, in the interest of time, I want to try and finish this lecture today. Same C tier and N. They're putting the objects, or they're putting the robot's arm at a slightly different initial condition. Doesn't know. Oh, decided it was a sphere right at the end. There's a few cases here, I think. Maybe gets it right at the end, but there's periods where it's not quite sure. There's one. Oh, nope. That one it's sure of. That's an ellipsoid. Ellipsoid, no, sphere, right? So it's still unsure sometimes.
Just because it was deciding what it was, do we know what they actually were there?
If you watch the video several times very carefully. It's hard. You can probably figure out if you watch. Good homework assignment for today. Go watch the videos. We got one more slide. I think we'll do that on Tuesday. You have a quiz due tonight. Good luck with assignment 5. Have a good day.